Hello everyone. So this will be a supplementary video for chain rule. So there's something more about just chain rule. I want to talk more about implicit differentiation. So this is more on implicit differentiation. Recall that implicit function, just like for example in R2, we have this x squared plus y squared equals 1, and I want to find like dy dx. What is this? And sometimes we can take derivative on both sides. So this is how we do it before. So we just do like d dx, x squared plus, like this is y. We treat that as y of x and y squared and equal like d dx 1. So this will be 2x plus 2y dy dx and equals 0 and blah, 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 go on. So this is implicit differentiation. This is implicit differentiation. So we do the exact same thing in partial derivatives. For example, like x squared plus y squared plus z squared equals 1. I want to find what is partial z, partial x. So we do the exact same thing, but now we write z in terms of x and y. So it's like this, partial x, x squared, y squared, plus z of xy squared. So z is a function of x and y and equals partial x, 1. And keep going. So this is the old way we do partial differentiation. This is good. This is really good. This is really good. But maybe we can have something even quicker. So recall that if we have something like this, x squared plus y squared equals 1, we can write this fxy equals x squared plus y squared minus 1 and equals 0. So this is a two variable function, or you can think about this as a level curve of the surface y equals x squared plus y squared minus 1. This is a level curve. So we can do the same thing for function of three variables. So now if we have this, if we have implicit function and implicit function, in function of three variables, so this is f, x, y, z equals 0. So we can write that this way. So for example, the previous case, this will just be f x y z equals x squared plus y squared plus z squared minus 1 equals 0. So we can treat that as a function, but the function equals 0. So we can treat that this guy is a function, say w or something, or f. We just keep it f. So if I want to find a derivative of something, maybe we can use chain rule to do this. So now this is our f. F depends on x and y and z. And recall that we treat z as z equals like zxy. So z depends on x and y. So now we have two layers, so x and y. Okay? So if I want to find fx, or maybe we write, maybe in terms of like confusion, maybe I write this equals w, a function w. So if I want to find partial w, partial x, but now w is 0, so this is partial x, 0. So it's happily 0 on the left-hand side. But by the chain rule, we can write this. W is fxyz, so this is w, so this is w. I'll keep it this way. So if I want to find x, this is one path. This is one path. The second path is this path. Right? So by chain rule, we have this guy will be partial f, partial x, and plus partial f, partial z times partial z, partial x. So this is we're using the chain rule, but now we have two layers. So happily we'll have this fx plus fz times zx equals 0. So that's what we want. We want to find zx. This is our ultimate goal. So finally we have this guy zx will be negative fx over fz. That's it. So this is another formula. If you use this, if you use this chain rule, we can happily have this formula. We don't have to take derivative on both sides. Then we just apply this formula. Then we have LZX. And that's it. And that's it. But the only case this has to happen is that we have to make sure this guy is non-zero. It has to be non-zero. It has to be non-zero. Okay? So if the question wants to ask you this, you can use this formula as well. So similarly, we can generalize this into multivariable function. So I already typed it out. So this is the three cases. So this is general chain rule, or you can use the dependence chart. This is using the general chain rule. We have this. So we have this step formula. So if we have general multivariables, so more variables, the calculation still hold. So fx1 to xn equals 0. So xn will be the function of all the previous one. So by the chain rule, this will be 1, this will be all be 0. Or you can do the exact same thing I did before. So by the dependence chart, this will be f. This is x1, x2, x3, and go on. And this is xn. But xn is dependent on x1, x2, to up to xn minus 1. So if I want to find this, this is my only two path. This is my only two path I can have. That's it. So we can have the exact same thing. We can have the exact same thing. We can have the exact same thing. So partial xn, partial x1 will be negative partial f. Maybe I'll just write fx1. So fx1 over fxn. If fxn is not 0. Okay? So this is some formula worth memorizing, but we don't have time to cover in our regular class. This is in the textbook, so you can read that, or you can use that. You can use that in the midterm. It's fine. It's fine. You can use that in the midterm, in the final, in any quiz. This is fine. Basically, you are doing the exact same thing. If you take the derivative on both sides, basically you are doing the same thing. I just do rewrite as a formula. Okay, so let's do it. And sometimes it'll be much more easier to do it this way. So we can see in the next example. So first of all, we want to do the implicit differentiation, so we have to write out our implicit function. So in this case, fxy will be x to the power 3 minus xy plus y squared minus cosine x squared y equals 0. So even though this is the function of y and x, we can always write this. So partial, so dy dx is just partial y partial x. By the formula, it will be negative x fx over fy. This is my formula. This is my formula. So fx, we'll just do the calculation. So it'll be negative. Fx will be the first term, 3x squared. Second term, minus y, plus 0, and plus. So cosine becomes sine x squared y times 2xy. This is fx. And we do the same thing to fy. So there'll be 0 minus x plus 2y. So again, will become sine x squared y, but now I have to time x squared. That's it. So easy. We just do this. We directly have the answer. We don't have to take direction on both sides and moving things around and rewrite y in terms of x and do chain rule, partial rule, and product rule, and whatever. Now we just take it. Taking partial derivative will be way easier than doing product rule, chain rule, or something. I hope so. I hope so. So this is something that we make things somehow easier to do. So similarly, if fx equals fz equals xyz, I want to find zx. So again, now it's three variable, xyz will become ez minus xyz. So by the formula, zx will just be negative fx over fz. So how to memorize it? It just, okay, the thing we want to do here, go to denominator. And the thing we want to take derivative, go to numerator. This is how we memorize it, So in this case, this is easy to differentiate, so negative. So fx, so everything, we only care about x, so first term 0, and minus yz. And now I want to take fz, so ez, still ez, and this will be minus xy. So we're done. That's it. So if you have this formula, everything is somehow easier. Of course, you can do the old way. You can do the old way. They'll give you the same answer, but this is quicker. I hope so. And next, what about this one? So now I'm not doing zx. So this one is slightly different. So you can guess the formula. So if fxyz is z to the power 3 minus xy plus yz plus y to the power 3 minus 2 equals 0. So I say that zy will become negative. This guy z will go to the denominator, so fz. And this guy, we want to take differentiation, so it's going to be the numerator. This is the formula. So if we have this formula, then we can directly take derivative. So fy, so it will be 0 minus x plus z plus 3y squared. So this is negative. And fz will be 3z squared minus 0 plus y plus 0 minus 0. And that's it. So this is the final answer. That's it. So this is the interesting thing. So why we can do zy? So this is the much more general thing. So in the previous cases, we say that, okay, z is a function of xy. But how do we know that? This is the question. So this is general. We call it implicit function theorem. So it's a big theorem. So the idea is just that if we only write this like something equals 0, like how do we know z is in terms of xy or something like that? Why we cannot write y in terms of xz or x in terms of yz? So if that's different, so this will change our dependence chart. This will change our dependence chart. So if we have f, this is x, y, z. We did this. But why we cannot write this? Like y is in terms of x and z, something like this. The answer is yes, we can write this. The answer is yes. Only when fx not equals 0, fy not equals 0, fz not equals 0. So basically the idea is that if this thing is not 0, then z can be written as a function of xy. So if fx is not 0, if xx is not 0, then x can be written as x in terms of y and z. If fy is not 0, then y can be written in terms of x and z. Then we'll have the partial derivative. So this is called an implicit function theorem. We cannot prove it here. It's really difficult to prove. It's a really important thing in mathematics, in higher mathematics. So sometimes we don't know how to write implicit differentiation. We don't know how to find the dependency of the variables. Then we use the implicit function theorem. So these are some introduction. You can read that. So basically the idea is that if this guy is not 0, then we have a function in terms of x and y. It's similar to different things. So you can change the variable to different things. Then we can use the chain rule, then we have this thing. So that's it. So that's it. So basically, why we cannot have 0? So implicit function means that, okay, it's locally look like a function. So we cannot let it be 0. So if you remember for the second variable case, x squared plus y squared equals 1, then fxy equals x squared plus y squared minus 1 equals 0. So I want to, then we can, if that is not 0, if fy is not 0, then y can be right in terms of x, the function of x. But how can that happen? Why do we need this? 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 The idea is just that, okay, if you remember in two variable case, that is the slope. So if slope does not exist, then everything. So if this guy equals 0, the slope go to infinity. Infinity means that it's a horizontal, it's a vertical line. So if you see the graph, this is the circle graph. This is on the circle is fxy equals 0. If we have a vertical tangent here, vertical tangent line here, this line, no matter how close you write this curve, this one, it won't never be a function of x. So no matter how small that is, it won't pass the vertical line test. No matter how small, no matter how small. So this point is when fy equals 0. So in this point, no matter around this point, you cannot pass the vertical line test. So it cannot be a function of x. So that's why we need that. So similar to fx equals 0, it'll be like function in terms. So you have to pass the horizontal line test, but it's just intuitive. You can think about that. And if this one, if around a point, so say a is this point, in this point, the vertical tangent and horizontal tangent, they are all not 0. So we can write that in terms of function of x and in terms of function of y. So that's the idea of implicit function theorem. It is not in the textbook, but yeah, you can read that. The idea is that this is not always true. It's just that, okay, we can make that happen, but we can also make different variable happen. And we will have different functions. We'll have different functions. So we can have y of x, we can have y of z. It's not always zx and zy. You can have different things. We only make sure the denominator is not 0. So if you look at this, we can happily write this out. So if I want to do this like xy, this will also be like fx negative fy. Only if this guy is not 0. Something like this. Something like this. So we can always do it like this. Or maybe yz. This will be f of y, f of z, negative. We can always have this if these two are not 0. If the denominator is not 0, we can always write different form of implicit function differentiation. So this is the theoretical background. The idea is that it's not always z in terms of xy. We can have different things. We'll have different dependency chart. Then by the chain rule, we can always have these different things. Okay? I promise you, this won't be in a midterm like more difficult cases, but yeah, this is something interesting to know. If you enjoy like differential geometry, this is the fundamental thing when we do differential geometry. Yeah. But that's a lot. That's a long thing to say. Yeah, so that's the supplement for implicit function theorem. I hope you enjoyed this. I'll see you in the next video.